want to take any more time. I want to ask Rick to get started, and I'm going to have Pat Mann, our program coordinator, go ahead and introduce Rick. So go right ahead, Pat. Thank you.
Okay, hi. Okay, hello everyone, and welcome to the June meeting. I don't think that we could have had a more fitting speaker for this evening, other than one of the most dedicated amateur astronomers and astrophotographers, Rick Bria. He is the Vice President of the Astronomical Society of Greenwich, and also a longtime member of the WAA. Rick is going to speak on the vital role of amateur astronomers towards the understanding of many facets characteristic of this universe. His own experience has been well documented in last month's newsletter under the article titled Nova Cassiopeia 2021, found on page 9. Incidentally, within the same issue, highlighted on page 1, is Rick's beautiful imagery of the silver coin galaxy. Rick, you are someone who really enjoys what he does. So let's give him a big, warm welcome.
All right.
Thank you very much.
Okay.
I can start sharing?
Yes, go right ahead, Rick.
Okay, and go. Okay, basically my talk is how I find it very rewarding, just as much as taking a pretty picture, to do, admittedly, a very small contribution to science. Somebody might use the data that we gather and do some sort of research, and perhaps we'll discover something. But I find it very rewarding, and I didn't think I would, but it is very rewarding to make these little contributions to science. So I thought I would share the different assets, the different facets, I should say, of the things I'm doing, in hopes that some people would maybe say that, hey, that's interesting too. So asteroid occultations, I'll start with that because I think that's the easiest thing. And when I say easiest, it's the least amount of time per night. An asteroid occultation will take seconds. So you could be set up to an asteroid occultation and then set down and go back to sleep if you want. Whereas the other things I'm going to talk about, they're hours long. So I'll start with the easiest and I'll go to the most lengthy observations. So asteroid occultations in combination with asteroid rotational light curves, which is another facet of it, that you watch the asteroid during the night as it's rotating, and you put this, it gets brighter and dimmer as it's as it rotates, because most of these things are not spherical. Anything less than say 200 miles across won't be spherical. Gravity hasn't had a chance to, there's not enough mass to pull it into a sphere. Combining occultations with these rotational light curves, we could refine the asteroid size, shape, orientation, orbit, and more importantly, or just as important, this thing called the Yorp effect, which is long-term changes in the orbit and rotation of small asteroids due to the way it radiates heat as it rotates. It gets heated up on one side and cooled on the other, and that radiation of heat goes out into space. It changes its orientation, it changes its orbit slightly over a long term. So it's not like it changes it overnight. Anyway, so that's what occultations are trying to do. And there's a bunch of free software that IOTA has that you could team up with people. And this is the kind of the neat thing. If it wasn't for this software, I don't think I'd be doing it. There's also a social aspect to it, because this software called a Cult Watcher, people will announce essentially that I'm going to observe this comet, this asteroid tonight. This is just one of many lines that'll be on the software. I'm just highlighting this one because it gives an idea of a reasonable event. So this blue area is the length of the shadow, and this notch here represents an observer, and this notch here represents where I am on the Earth. So based on where you are on the Earth, you'll be somewhere in this area. So you could determine immediately as you look in the software, this little blue screen, this little blue square will come up and let you know that you're somewhere in the shadow. This, by the way, is orange area is the first standard deviation of error, this essentially error bars of the prediction. Then second standard deviation, third standard deviation. So immediately you know someone's looking. You could then join and say, hey, I could join this person's observation. And of course, the more people you have, the more valuable the resulting information will be. And we'll talk about why that is in a bit. But it gives you all sorts of information, like the magnitude of the star, the altitude of the star, the maximum duration of the occultation, the magnitude drop when the asteroid blocks the distant star. This would be a large one, 5 magnitudes. Usually it's a lot less, but that you'd actually see occur if you were watching it on the video. But there's like half a dozen pieces of software that is free. You just need to get the hardware, and we'll go over what that is later. But so it's the software is all done. You just need the hardware, and if you're taking deep sky pictures like I am, you have most of the hardware anyway. You would just need to get a appropriate camera, and then join into asteroid occultations for you to decide to do so. Anyway, surprising to me, occultations are a potent tool to study asteroids. It can produce resolution in quotes exceeding any ground-based radio or optical observatory and the Hubble telescope. I know that probably raises some eyebrows, but those optical observatories will have a spatial resolution separating objects of about 30 milliarcseconds, where occultations you can get down to 3 milliarcseconds. Now, I'm not talking about producing a picture, but the separation of objects like a star and an asteroid. And so I'll go over how that works in a bit. So discoveries can include unknown double stars due to stepped disappearances and reappearances, and I'll go over how that works. And moonlets of asteroids, rings around asteroids, double asteroids, oddly shaped asteroids. Oh, I'm supposed to, beg your pardon, I'm supposed to do this, hide that. Contact binary asteroids and even craters in asteroids in a question mark. So let's see here. All right, so I'm talking about are asteroids a threat? I'm not talking about Armageddon or the movie Armageddon, and that we're going to save it. We're going to save the Earth or anything. But you might remember asteroid NY40 from 2002. It came. It's about a half-mile wide and came as close as the Earth, just beyond the orbit of the Moon. This is a picture I took from the Bowman Observatory. This line here is the asteroid moving among the stars in the matter of a few seconds of the exposure and through a telephoto lens. And then this new asteroid that everybody was talking about a while back, Apophis. It's a ½ kilometer wide, and it will come inside the orbit of our geosynchronous satellites in the year 2029, which is only about 20,000 miles away. And I was working before I retired, and this other worker came up to me and goes, "Hey, what about that? What about that rock that's going to hit the Earth?" I didn't know what he was talking about, because I knew about Apophis. We've seen it in Sky and Tell, and we've seen it in the literature. Yeah, it's going to hit the Earth. It's going to kill a lot of people. What are you talking about? So I finally figured out he's talking about this asteroid, and so of course it's not going to hit the Earth, but there was a small chance reported that in the year like 2029 or the year 2064, there was like a very small chance it was going to hit the Earth. But it turns out that we really didn't know accurately enough where it was to determine if it wasn't going to hit the Earth. Absolutely not. So IOTA took it upon itself to really go after that asteroid. And so here we see an observation that occurred on March 7th of this year. And all these lines are different people in different parts of the in the United States. And all their names are here and where they're located. And this represents the asteroid Apophis, about a half a kilometer in diameter. And 3 people watched it go beyond block a star for a given amount of time. And all these other people, we weren't sure where it was. So all these other people spaced about, I don't know, about 3 miles apart, got misses, as it's called. But the 3 positives help refine where the asteroid was, and that gets added to the information of where it is in its orbit. So the next time we observed it, now I wasn't part of that observation. That's not me. I wasn't in the right part of the United States to see it. But this is March 22nd, and you can see that they're narrowing down the search. They're closer now to each other, these people, and only one person got a disappearance reappearance, but again, it refines exactly where the asteroid is and exactly where it is in its orbit. So the following prediction on April 4th, these people are only separated by about 3/4 of a kilometer, and 3 people got the disappearance reappearance as it blocked a distant star. And so what's happening is we're figuring out better and better where this asteroid is. Here's the 4th observation on April 11th. And there was no misses because we pretty much know where that asteroid is now accurately. And so here's the result. Well, you look on Wikipedia, and it says on March 9th, 2021, using radar observations taken at Goldstone, and 3 positive detections of stellar occultation, Apophis became the asteroid with the most precisely measured Yarkovsky effect, which is that effect of the radiation cooling, and it's slightly moving that asteroid away from where we thought it was. And NASA says it's not a hazard for the next century. And they couldn't say that until these observations came into being. Some publications are reporting the occultation data, that that was the contribution of the occultation data, and some publications aren't even mentioning it. I just want to like we're kind of like the redheaded stepchild of data. But anyway, it was a pretty neat thing that occultations played a part in that. So these are the asteroids visited by spacecraft as of 2012. And you can see that they're oddly shaped. This is probably a big crater here, an ancient crater. This might be a crater in silhouette here. Some of these are comets, but some of them are asteroids. And so you can see that they're very, very oddly shaped. And we all know that, most of us know that most of the asteroids reside between Mars and Jupiter. And we actually view some of the trans-Neptunian objects too in occultations, but most of our observations are from the main asteroid belt. So here's what's going on when you do an occultation. You have a distant star, essentially at infinity. So it's a point source, and you have this asteroid, which is about 2 to 3 times Earth's sun distance, or 2 to 3 AUs, astronomical units. And the asteroid that you're trying to view is going to cast a shadow upon the Earth, the same shape of the asteroid. The shadow will be the same shape of the asteroid. If it's potato shaped, it's going to be a potato shaped shadow. If it's a double asteroid or whatever shape it is, long and thin, that's going to be the shadow shape upon the Earth. So you get people in different places, and they're going to see the asteroid either see the A person and the E person, they see misses as the asteroid moves this path. It's usually going from east to west because the Earth is going faster around the sun than the asteroids because they're farther away. But B, C, and D people see different length of durations because the asteroid is not, it's oddly shaped. B is going to see a shorter duration than C is, and C is going to see a longer duration than D is. So that's how if you get a bunch of people, that's how you determine the shape of an asteroid quite accurately, more accurate than the Hubble Space Telescope can do, and more accurate than radar can do. That's kind of a surprising thing to me, but it turns out it's true. And here's the observation that IOTA really went gangbusters on. A whole bunch of people started viewing this binary asteroid, and you can see that that there was people that were in between. Imagine being the people in between missing both asteroids, but very fantastic, a very important observation. I'm not going to pronounce these asteroids, but you can see the name up here. But it's an observation that's being requested by these professionals to check it out. All the different aspects of it, the orbit of how they orbit each other and all that stuff. So now I'm going to go to observations I've done, earth-shattering, and just as a joke. But this is an important observation that a professional amateur down in South America wanted, and it's the moon of Uranus, Umbriel, occulting a distant star. This distant star, of course, has a catalog number, but I didn't want to have a bunch of numbers here, so I'm calling it distant star. This is the planet Uranus, necessarily overexposed because it's a lot brighter than its moon Umbriel, which is invisible on this frame because it's just too faint. It's fainter than a distant star, and it's fainter than the moon Orion and Titania. And this represents, I'm locked on to 9 different geosynchronous satellites that's producing this rather accurate timestamp that's on every single frame of this video. This is, of course, a picture of the video. I'm not going to show the video. And these are sub-second timestamps, and this is the amount of frames that occurred since the start of the video. Anyway, this is a very, very difficult observation because it's next to a very bright object, namely Uranus. But we were able to do it, and so were a bunch of other people. And so this is what you end up with after you go through all the software. You're measuring the brightness of the asteroid and the distant star together. Of course, this is the twinkling of the star. It's going through the Earth's atmosphere, so it's undulating like nobody's business. And this is that scintillation we see when we look up and we see stars twinkling. And then the moon Umbriel covers the star, and you're just seeing the light from Umbriel. And then after 65, and this is a long observation, 65.93 seconds, the moon Umbriel uncovers the star, and then you're seeing the combined light of both of them again for that period. So it was a very neat observation because it's very unique. You usually, like I say, they're 1 second, 6 second occultations when you're talking about an asteroid, but in this case, it was a moon that is about 1,200 kilometers across. This is the silhouette we get. Some people are not using as good equipment as we are, so they have these wide error bars. And I don't know how observer number 8 came to this conclusion, but anyway, this doctor, I get a load of this name, Dr. Altair Gomez. He's the gentleman from South America, and he was really wanted this information and asked IOTA to contribute, and we did. And so he's going to compare the data of this event with the Voyager spacecraft data from 1986. It's hard to believe, but we haven't been near Uranus since 1986. So it's kind of important. This 6 line here represents where the predicted center of the moon should have been. So it's off by a couple hundred kilometers probably. And where our observation is this, I want to say a gum colored line here, sandwiched between a bunch of other lines. Here's our Bria near Greenwich. And so we had a very good observation. Our error bars are very small. And so when you add all this up, someone's going to diagnose this and come to some conclusions, maybe adjust the size of the moon, or adjust the position. I'm not sure what he wants to analyze, but this doctor here is analyzing something. But normally, this is I would call a normal occultation of asteroids. This is a thesis. The duration was 6.9 seconds. I'll show you in a second the video of this. Again, the scintillation from the star twinkling. The asteroid covers the star. You're just seeing the light of the star dimly, the light of the asteroid dimly, and then the asteroid uncovers the star, and then you're back to normal. Now, if this was a very close double star that was previously unknown, you'd get a stepped event. You'd first cover one star of the double star that was unknown, and you'd cover the other star. So you can discover unknown double stars accidentally just by doing an asteroid occultation. You thought the star was singular. We thought the star was singular, but it turned out to be a close double. Excuse me, let me stop this and show you the video real quick. I can't do it with that one. I got to do it with this one. Open with you. Hide this. Okay, in a minute, the numbers will go away on the bottom there. There it is. When this gets to 22, let me try to cheat this up a little bit. When it gets to 22:05, the time, the star near the cursor there, near the arrow, will be occulted by the asteroid, and you'll see it dim down really. You probably still see it, but it'll dim way down. 5, 4, 3, 2, 1, and then it's occulted. See, then a little asteroid is blocking a huge star. It's kind of amazing. And here we are. We're back again, and back to normal brightness. So that's the observation, and you run that through software, and you end up with a graph that you send in as data to IOTA, and then it gets published on the internet, and anybody can go and study it. Let's go back here, start from current slide. All right, so this is where we were. Okay, this is a very interesting observation that I did with a student, and it's a double event. So you have the asteroid with the star. The asteroid blocks the star, and then for about 2 seconds, it unblocks the star, and then it blocks it again, and then unblocks it. So what the heck was happening there? So if it unblocked it way out here, it would probably be a moonlet of the main asteroid, but it blocked it really quick. And so the conclusion was we had a graze. The center of the asteroid was predicted to be here, but it was off by about 50 kilometers. The asteroid is about 110 kilometers in diameter. So the center of the asteroid is down here, and we're on the very edge of the asteroid. So we get a double event. Another observer from Westport was supposed to be here, but he had equipment problems. So we're the only viewers of this asteroid. So we had a disappearance, a gap, and then another disappearance. I went into Photoshop, and I carved up the asteroid so that it represents more accurately what it should be if our event is true, and it was calculated that it is statistically. So this is a notch in this asteroid that we don't know about. I'll go back and forth a little bit. And it could be a giant crater that as you saw in those other pictures, these things have huge craters on them. Or it could be that this is two pieces of two different asteroids stuck together, and that's a valley. We don't know anything about that, but it is an interesting result. I thought it was kind of fascinating. And again, we don't get to name that. That's not like the student with me was Catherine May. It's not, you can't name it like Catherine's crater or anything like that, or the Mary Aloysia Hardy crater. But we're happy to donate that information to the database, and someday maybe, you know, if you're lucky, that'll come to play in somebody's research. Anyway, this is the equipment I use. I use a Wattec 910X HX, and it is the best, unknowns to me. When I bought it, I didn't know anything about these sort of cameras. It's an analog camera, that, you know, an analog video camera that's mainly used for security. And it's the pinnacle of analog cameras for asteroids. The IOTA VTI is a video time inserter, that thing that was making the timestamps on the bottom of the video frames. That locks onto geosynchronous satellites, and that costs $250. You need something to take the analog signal and put it into your computer, so you use a USB video to USB converter and adapters and cables, power supply. The occultation software is free, about $1,000, and your telescope and a laptop. But you don't have to do that. You could do, IOTA has a kit that they use. They went to a video manufacturer, and they say, hey, could you modify this a little bit for what we're doing? We're doing asteroids, and they did, and it's called the Night Eagle 2. And it's you can get everything I just told you. That cost $1,000 for 530. So for $530, your telescope and a laptop, you could do it. Not that it's for everyone, but just in case it interests anybody, I think it's a very rewarding thing. It's kind of a cool thing. So on the horizon, there's that new Gaia catalog. Some of it's been released, but believe it or not, not all of the data from the Gaia catalog has been released, especially stuff that pertains to asteroids. And when it's finally released and finally integrated into our software, we're going to be able to do smaller and smaller asteroids, never before observed asteroids, and of course, fewer misses. The last thing you want to do is go out 3 in the morning, and the software, by the way, predicts your percentage of success. And so it'll say you got an 89% chance of success, and you get a miss. So in 3 in the morning, you didn't want to do that. Misses are almost a thing of the past already, and they're going to be a thing of the past soon when the Gaia catalog, the full stuff, gets released to the public, and we can incorporate it into the software. It's not done yet, but there's new cloud-based IOTA software where you don't have to have your computer. You could just get on anything on the internet and go to the website, and you could see cloud-based software, predictions of where you are, signing up for events and all that stuff. The software we're using is very good, but you have to have it on your computer. And sometimes you're at work, or you can't get to a computer, and you want to see what's going on tonight. You can't do it, but in cloud-based software, you could be anywhere and anywhere in the world and go and see. New cameras, of course, are always coming out, promise improvement performance. So the future is looking bright, and I'm very happy about that, because I think it's a neat thing. So it's the International Occultation Timing Association, and they use data from the Minor Planet Center to predict the orbits of the asteroids. And of course, it's always getting better as we make better and better observations of these things. So I'm gonna stop that, and I have 2 more. So that was asteroids, and let's go on to variable stars. Okay, the AAVSO has a whole bunch of things that they do. You might just think of them as observing variable stars, but they observe anything that's variable, supernova, and now they're doing spectroscopy. They do exoplanets. But in this presentation, they'll be on exoplanets in a minute. But this is just about stuff they do with variable stars, which is a lot more interesting than I thought it would be. I heard about the AAVSO in the 80s, but I didn't join them until recently, last couple of years. So stars vary in brightness for many reasons. Some vary in brightness because one star eclipses another. So it's called an eclipsing binary. And so back in 2017, with a student, I delved into that. This is a long observation. There's a 3-minute cadence. So every blue dot you see there, which represents the dimming of a star and a brightening of a star, because one's eclipsing another. They're 3 minutes apart. You add that together, this is several hours. It's probably like a 4-hour or so observation. So one star is blocking another, you get this V shape, gets down here and starts unblocking, and you get this return to normal brightness. So out here, you're seeing both brightness of each stars added together. And down here, you're seeing where one has blocked the other. And this represents a background or reference star. So this is called, what do you call it? Differential photometry. We're measuring the star measured against a reference star. It's called differential photometry. Photometry is the measure of the brightness of something, and so if there was anything, if this was a result of clouds or anything other atmospheric phenomena, it would show up in this background star, which we use as a reference. So it was a very interesting observation. I want to show you a simulator I found online, which is, I think it's fantastic. Where did that go? Oh, you son of a gun. I'm not seeing it. It was there the other night. Let's see if I can just find the. Okay, I beg your pardon. Well, I can't do it. Okay, well, anyway, it comes from the University of Nevada. You son of a gun. And you could model the system. You could make stars bigger, smaller, and all different angles, and you could see the one eclipsing another. That's driving me crazy. Anyway, I could show it to you when I get to the exoplanet talk, but for some reason it's missing here. Okay, so there's also spectroscopy. Let me do this from current slide and hide this. Also, I've recently dabbled in spectroscopy, which the AAVSO has a database of two. So they have a database of variable stars where anybody can go in doing research and grab the data and discover all kinds of neat things like how mass transfers from one star to another and changes the brightness of it and all that stuff. But this is spectroscopy that they also have a database of. And this is the star Vega. And I use a thing called a grism, which is a grating that breaks the light of the star up into a rainbow. And so you see to the right here, you have blue, green, and red. You might see these little gaps. I hope they're showing up on the screen, but you see these little gaps, and they're called absorption lines. And those absorption lines occur when you have a bright light source shining through a cooler gas. And whatever that gas element is, it's going to block a certain wavelength of the spectrum of light. In this case, it's hydrogen. It's going to block certain wavelengths of that spectrum. And you'll be able to tell what's in the atmosphere of that star based on these absorption features. You start off with something like this, you run it through software, and you end up with a graph like this, where it shows the simulated spectrum down here. And you end up with what's called a 2D graph, a two-dimensional graph of what you're seeing up here. So this absorption line is represented here. The one over here is represented here. And the one way over in the red is represented here. They're all done by hydrogen alpha, hydrogen beta, and hydrogen gamma, different states of the same element. Over here, you get these little blockages when the light comes through the Earth's atmosphere. You get these little dips where that part of the spectrum gets absorbed by the Earth's atmosphere. So in this case, it's hydrogen. In this case, it's an A star type, spectral type A, main sequence. So this is kind of like a normal spectrum. If it was an M star, the hottest stars are O, and it goes down O, B, F, G, K, M. If it was an M star, there'd be very little in the blue end of the spectrum. It's hotter over here. There's more energetic stars radiate in the blue, and you'd get a peak in the red where it's like a M dwarf star. You would get. Our sun is kind of in the middle. It's a G star, G2. Anyway, this is a normal one. I'm going to show you some really wild ones, really abnormal ones that I think are kind of cool. So if you were doing photometry and for the AVSO site, this is 2013 Nova Delphinius. On August 24th, it was at magnitude 6, this bright one in the middle. In October of the same year, it went down to magnitude 11 after you had an explosion, got really bright, and then it dims over here. It's way down to magnitude 11. If you were doing actual observation here, you would have a map with comparison stars of known brightness, and you'd be saying, okay, this one is such and such a brightness, and this is brighter than that, and that's how they do it. And you can do a visual observation, be accurate between 1/10 or 2/10 of a magnitude. Or you could do with a digital camera, and you could run it through the software similar to what I ran it through in this binary star system. Yet the software will end up telling you what the magnitude is. Here it's 6.2 up here and 7.8 down there. And then you would run it through the software, figure out the magnitude, and then submit your observation to the AVSO. You can do it visually, you could do it through the CCD camera. So that would be the methodology for that. And here's the NovaCast of this year. You can see I could tell you this is a magnitude 9 star, this is a magnitude 6 star. If you were doing this one, you would again have other stars in the field with of known magnitude, and you would do your estimate there. Or you would do it through CCD photometry and run it through software, put a measuring aperture on it, and the software would spit out the data for you, and then you send that off to the database. Also, at the same night, I had two telescopes, 2 cameras going. This was through the C14. CDK14. I also had the refractor going with the GRISM, getting the spectrum of it. It's much better to do it in black and white than color because you have better resolution. And in this case, you don't see a continuum as you did with the normal star. You see these bright knots that are emission features. Of course, this is a nova when it just exploded. This a white dwarf had this material on it that exploded in a violent nuclear runaway explosion. And so you get these emission features, these spikes, hydrogen, some helium, some sodium, but helium and hydrogen, you get these, and you could look at this spectrum down here in color, where you get these peaks of brightness of emission rather than absorption. But interestingly enough, this is a classical nova where a white dwarf sucked the material off of a nearby star, and then it built up on the surface of the white dwarf and blew up. The white dwarf remains, but the material that built up on it had this explosion. So you got, in your mind's eye now, you gotta think that there's this expanding shell of gas flying away from this star. Sometimes it could exceed 2,500 kilometers a second. So now in your mind's eye, you got to remember that, okay, this shell is expanding and some of it is coming right at the Earth. Not that it's going to reach the Earth, but it's aimed right at the Earth. And anything that's coming at the Earth will be blue shifted. Anything that's going away from the Earth is going to be red shifted. But there is some material that's coming right at the Earth, and that produces what is known as a P Cygni profile. And what that is you see this peak, and to the left is a blue shifted, so the peak is emission, but to the left is a blue shifted absorption feature. So you have the peak here, the bright spot. To the left is a blue shifted absorption feature from material going right at the Earth. Same thing over here. You get a peak of hydrogen, and then you get a trough of absorption. Here too, peak of hydrogen, trough of absorption. And if you measure the distance from the peak to the trough, you could tell how fast the material is coming at the Earth. So that's kind of fascinating to me, that with an 85 millimeter teleview telescope, you could of course use a bigger telescope. And this grism that looks like a filter that you screw into an eyepiece. It's just 1.25 inches diameter. And it literally screws into your eyepiece if you want to do visual, but I have it hooked up to a camera. You could essentially determine and people have, you can go on the AVSO site and see what their predictions are. And of course, you watch it getting slower and slower as time goes by, and the gases are expanding out into space. They're slowing down. And so at a certain date, they're going a certain speed, and later on, they're going slower. And these amateurs are determining the speed of this expansion of this material coming off of the star. And I think it's pretty wild. So this is a 5-second exposure times a stack of 22, in case anybody was interested, but not any long all-night thing. It's just you take the data, you run it through this software called RSpec, and you end up with a kind of neat a result like this. I think it's fascinating that with the minimal of equipment, you could do something like this. And this is actually the star that was called the P Cygni profile, but this is the star P Cygni. And what it is a rare luminous blue variable, LBV, over 5,000 light years away, and can be mistaken for a nova due to the similar spectrum. Look at the spectrums are very similar. The peaks are in the same place. You have helium, so you don't have sodium, but you have helium and hydrogen in the same places. But this is the star that, and I don't have an accurate enough resolution to show the troughs in this one. I had it in the nova because it's expanding at a much larger, faster rate than in a star like this. But this is a huge star that's again expelling a huge amount of shell of gas via stellar wind, and the theory is it eventually becomes a Wolf-Rayet star, which I'll show you in a minute, and then it'll become a supernova. But again, a very interesting thing that it has emission lines rather than absorption lines, because it's hot gases being expelled from the star. Really a star that would dwarf our sun. This is a Wolf-Rayet star, and again, they're pretty rare, but it's this star in the center of the Crescent Nebula. And this gas has been expelled from it, several masses of the sun, equivalent to several masses of the sun. out into space at a high speed and colliding with gases at rest. And you end up with this kind of a weird spectrum, which is way over in the blue, because this is hot. This star is extremely hot. It's WR 136. There's only a few of them that we could see in our galaxy, and a few of them reside in the constellation of Cygnus, and this one is no exception, because it's in the constellation of Cygnus, right in the center of the Crescent Nebula. So extremely hot, strong stellar winds, and it fuses helium. Now you see helium peaking, very little hydrogen. You got nitrogen, you got carbon, you got helium, nitrogen, but you don't see any hydrogen, because it blew off its hydrogen shell out into space. And there's a lot of sub categories to this, depending on what you think of a star as a bunch of an onion shell, and it's got a hydrogen shell, a helium shell, down carbon, oxygen, all the way down to nitrogen. So it depends on what shell is being exposed as to what this could be a huge peak of carbon if the carbon was exposed, or nitrogen if the nitrogen shell was exposed. In this case, it's helium, and so it's a completely different looking spectrum than anything we've seen so far. I thought it was pretty fascinating. This was a 10-second exposure times 22. So the device I use is it's from a company called Field Tested Systems. It's a star analyzer grading, RSpec software, adapters, about $500 in your telescope and camera, and you're off to the races doing something like that. Again, fascinating. I find it very rewarding. So in case anybody was interested, and by the way, I have all kinds of information of documentation and how to do it. If anybody wanted to get started, I could certainly help out. So now we'll talk about exoplanets. Get rid of this. Exoplanets. Again, AFVSO have an exoplanet section. Exoplanets, and a couple of people might recognize this picture that came with me when we went to look at the Venus transit. But exoplanets are discovered via the transit method. Here we have Venus transiting the sun. It's blocking a small percentage of the light from the sun. Here we have Mercury transiting the sun. It's blocking a small percentage. But we can't see planets orbiting different distant stars, a planet that size. We have to see large planets orbiting distant stars, because they block enough of the light to be detected from the distances we're detecting them from. In this case, I'll show you an example of 700 light years. But here's the method. A distant planet comes around and blocks a given amount of the light of the distant star. And we're measuring the brightness over time, and we see the dip as it goes in front of the star and has a round bottom for a specific reason. And then we see it unblock the star as it comes out the other end. And the round bottom is very important. The round bottom is because of darkening at the limb. You see darkening at the limb on the sun. You see darkening at the limb here on the sun. You see darkening at the limb of all stars. And that's because the light coming from this area of the sun has to travel through the atmosphere of the sun to get here. So it travels through less atmosphere here than it does here. So you have darkening at the limb. So you get this round bottom. This is important when you're trying to determine if it's an exoplanet. Is it a star spot, or is it one star blocking another star? The other star blocking the other star gives you that V. It doesn't give you the rounded bottom like you get here. So it's important when you're trying to determine what you're seeing. But here's WASP 39b. This is the star I observed. Actually, the planet. WASP 39 is the name of the star. B is the name of the planet. It's not like in Star Trek where they go, oh, we're orbiting Rigel 4, which would be the fourth planet in this Rigel system. Well, the AA, the astronomical community, didn't take up that system. The system is the planets are letters, and there is no A planet. There's only B, C, D, E, F, if you have that many planets. So this WASP 39b is the first planet orbiting WASP 39. WASP stands for Wide Angle Search for Planets. Of course, these are artists or renditions of what they think the planet looks like. Exoplanet events are timed to BJD TDB. It's a new kind of timing that I never heard of until recently. It's called barycentric Julian date, barycentric dynamical time, Astro Image J. It's free software that determines that for you. And what that is the barycenter, the gravitational barycenter of our solar system. So it's not timed to the center of the sun, which would be heliocentric. It's time to where the gravitational center of the solar system is. So as the Jupiter and Saturn mainly pull on the sun, it doesn't stay in the same place. It gets pulled around a little bit. And so based on what year you're viewing, and this comes from 1945 to 1994, the barycenter is going to be different places. Sometimes it's within the center of the within the boundaries of the sun. And sometimes it's external from the center of the sun. I think it's overkill myself, but that's what the decision has been made. We time it to the barycenter of the solar system, which is labeled BJD TDB. So Astro Image J calibrates and performs does everything. It calibrates all your data, your darks, your flats, your images, and performs differential photometry, computes BJD TDB of your event, and it also computes the radius of the exoplanet, the orbit radius, the inclination of the orbit, the transit center, and the duration. It does that all for you. It does take some getting used to, but I have all documentation, and so does IOTA. IOTA has documentation. They call it the cookbook. It tells you what to click, when to click it, and how to process your data. What you do is you place measuring apertures. This is one field of one picture of I took 360 pictures of that night of the event. T1 is target one. There's a star in here. I placed an aperture. And these are two comparison stars, they labeled C2 and C3. And differential photometry compares the comparison stars to the target star, and you end up with what's called a light curve, which you'll see in a second. This is the software that we use, and you end up with this. This is the result you're looking for, which is a light curve of the transit. So what you have here is they call it relative flux, which is basically brightness over time. Each dot represents a 33-second exposure through a 16-inch telescope with the camera we borrowed from Stanford Observatory, which is an STL-11K. So we guided on this exoplanet, this star all night, and so each dot is a representative brightness, and you can see that it dimmed as the planet went in front. It has a round bottom, and it undimmed as the planet came out from in front of the star, and then of course it went back to normal. Out here is called the wings. You want at least 30 minutes out here. I actually had some equipment problems. I started late, but it turned out the vent also started late, so it all worked out for me, luckily. If you can't be good, be lucky. Down here, it represents the comparison stars, and you see that they're, except for one, they remain pretty steady. In other words, there wasn't any clouds or anything like that. I got lucky, and it was a good night. There was no clouds. It was clear the whole night, and you have to have that because it's about 4+ hours observation. So it's 360 is a target star. This is WASP 39, and this is the catalog number, the observation run. Down here represents the air mass. And of course, over 4+ hours, a star is going to move in our sky. It's going to rise to a certain point, reach its height of where it's going to be that night, and then it's going to start setting. So this second line here is the computed, by Astronomers, the computed transit, calculating in the air mass change. So you can see it's widespread of a scatter here, and it gets a little bit more condensed here. So that's the software kind of computing where the event was. Also, you might notice that this is the predicted ingress and predicted egress of the planet, and it doesn't align up to my observation. This is back in 2017. And so for the longest time, I couldn't figure out what I did wrong. I had to do something wrong. By down here, the time of calculated by the barycentric TDB time, not universal time. And you might notice that it's about 2% drop, a little over 2% in brightness. This would be 100% and 98%. But I was banging my head against the wall trying to figure out why I'm late on the prediction. I thought it should be perfect, but it turned out that it wasn't an error on my part. It was that and this is the reason why the AAVSO wants us to do the observations in the first place, and NASA wants us to do the observations in the first place, because the original orbit period was predicted off by 1.6 seconds. And so it's been 7 years. This is my observation here, and these are all other observations other people have done. So you see there's a slope here. The bigger circles represent a higher quality than these smaller circles of observation. Better signal to noise, better equipment used. There's a slope here that says, and this is 0.01 of a day. This is observed versus calculated O minus C. Down here is epoch. These are orbits of the planet around the star. So it's probably about 620 orbits since it was discovered. So if you add up 1.6 seconds over 620 orbits, you can end up with about 16 minutes of error, which is about a little over 0.1 of a day. So I was worried for nothing. This is what, and I didn't know, this is what I figured the prediction would be bang on. The prediction was off, and this is why they want, it's called the transit time variation. This is what the telescope satellite TESS needs. It gets all these candidates and even confirmations of exoplanets, but they need follow-up observations to see if there's transit time variations. Have they missed something? Is it even an exoplanet? Because remember, it could be a false positive if there's a binary star there. This test doesn't have the resolution to determine if there's a binary star in the system or if it's an exoplanet or what it is. Sometimes it does, sometimes it doesn't. So there's a list of stars that AAVSO wants you to observe, and so you would go to that list and you pick out one, and you do the observation and you send it in, and it goes to a big database, and the hope is that some professional astronomer or amateur astronomer doing some student doing research go into that data and figure out something from the data that you supplied. So it took about 170 minutes for the transit to complete, and it was only about a 2% drop. And so the software spit out that the planet WAP39b is 30% larger than Jupiter, orbits a star about the size of the sun in 4 days, so it's years, 4 days long. And so this is what it spits out, and I found it really, I think it's one of the 10 best things I've ever done astronomically. I think it was really cool. I haven't done one since because we redid our observatory, and we did it in the hope that we would be doing exoplanets. So we got fork mount just for that reason, because you don't have to worry about meridian flip when you get to the meridian. You're tracking this thing for at least 4 hours, if not longer. This is that exoplanets. This is that simulator you can get at the at that school has that website, University of Nevada. And if you put in my results, by the way, it tells you the inclination. Do I have that here? Don't have that it has an inclination. Maybe I said it before, I'm not sure. Not only does it tell you the radius of the planet and the radius of the orbit, it also tells you the inclination. And I couldn't figure out, how could it figure out what the inclination of the orbit was? And that's because if it's in different places, there would be, it wouldn't fit mathematically. Remember, there's laws of orbital motion that if it goes around at a certain period, it has to be in a certain place. If it was up here, it wouldn't match the inclination because the event would take too long. So if the event takes a certain amount of time, there has to be a certain inclination. So I could never figure that out, how until you play with this program. And I figured, oh, well, that's how they figure out the inclination, because it would take a certain amount of time based on the orbital period and the size of the planet. It has to have, if it takes a given amount of time, and if you play with this information, this changes, of course. You can't put a bigger number than 250 of observations. I had 360. But anyway, it worked out that I could figure out that's how they figure out the inclinations. So my observation basically looked like this. Of course, you don't see this, you just see numbers. You see this. But when you play with this simulator, you can say, okay, this is basically the size of the star relative to the planet. And this is the inclination. It's not 90 degrees right down the middle. It's a little bit lower than 90 degrees. So I thought that was kind of cool too. And that's the end of my presentation. I guess I don't know if we do question and answer, or
Yes, Rick, we can go ahead and entertain any questions. Anybody that has a question to pose to Rick, please.
I know there was a lot to absorb, but sorry about that.
No, it's great to see your the way you present the data, and just to connect the video of seeing the decrease in the brightness of the star and how you translate that to an actual measurement of the light output. So any questions? Anybody have anything for Rick?
Yeah, Rick, when you use the TeleView 85 and the GRISM and the ASI 290, do you use a focal reducer on that, or you just take it straight?
No focal reducer. No, it's native. I think it's I think it's F7. Yeah, and it's and you don't want to be below like F7 when you're using a GRISM, because it changes the dispersion of the GRISM. And of course you got to find a happy medium of the spacing between the GRISM and the recording CCD. Right. If it's too big, it disperses it too much, and you don't get any real gain in resolution, but you dim the resulting spectrum so much that your exposures have to get longer for no reason. In fact, that's the beauty of the GRISM, is you can go after fainter stuff than people can with these really advanced spectrographs, because they can't go after, they're limited because they have so much spectral resolution. They dim things so much that they can't go after the really faint stuff. So there's a guy that does supernova classifications with a star analyzer before they can do it with these big spectrographs, because he can go so faint so quick. It takes them a while to get it, and he's going on these databases, and he's classifying supernova before they do with the big guns, because he could do it so quick, because he's not doing this. Of course, you can't do things that they can do too, but he could do these novas before they can do it with the big expensive things. Anybody else have any questions?
Anything else? Rick? Well,
Well, if not, I tell you, I get just as much satisfaction as doing this sort of thing as I do taking a pretty picture. So if anybody needs any help at all getting involved, don't hesitate to contact me because it's very rewarding. And if you told me I was going to do observe a planet circling a star 700 light years away, if you told me that years ago, I thought you were nuts. But it's possible through the transit method, which I thought the transit method was nuts when they announced it. I said, that isn't going to work. These people are crazy. But it not only works, we've got thousands of exoplanets now that we never had due to the transit method.
Rick, I have a question. It's
Sure.
Anne Safola. I just wanted to know, do the troughs only happen, if the Earth is there, or is there any other period where you see spikes and troughs together?
You see spikes and troughs through both those very energetic P Cygni stars, which is these blue, luminous blue variables. But you do have to have enough resolution, because anytime gases are headed right toward the Earth, you'll get that trough, which is called the P Cygni profile. And you should have seen it in my P Cygni picture, but I didn't. I'm just getting to the point where I'm getting the right resolution out of the equipment I have. There's other things I want to try. I want to try different telescopes. I want to try different dispersions. The farther away you get the grism from your CCD, the wider the dispersion. So I'm trying to find the happy medium of where I want the dispersion to be. But anytime gases are headed right toward the Earth, whether it be a nova or this luminous, whether it be the P Cygni or even the Wolf-Rayet stars, depends on how fast it's heading toward the Earth, if you have the resolution to see it. But you should have seen it in the P Cygni star too, because that's where it was discovered. But I didn't have the resolution to do it at that point. Maybe in a little bit.
Hey Rick, it's Mike Safola. Do our rovers on Mars, are they doing some of this kind of science, or are they getting these with these signals coming directly to them as opposed to Earth, and recording troughs and recording the spectrums?
Not that I know of, but as a side note, that New York 40 asteroid that you saw, that picture I showed, that was done with the camera I bought from you. I bought that camera from you a long time ago, just hooked up to a telephoto. But no, I don't know anything. I don't know anything of happening on Mars with those rovers. No, I don't know.
Gee, Rick, I was just going to say I need that back, but that's all right. You're doing better things with it than I'd ever do. But that's interesting. I'd be curious if they're picking up any of those doing any of that same kind of science. Obviously, they have finding water and life on their target, but
right. Anybody else have any questions?
All right. Well, Rick, that's great. Thank you for all the time you put in putting that together. I'm sorry we didn't get to see some of the pictures. Do you have a chance to share that photo that you had, that background of the Mary Aloysia Hardy Observatory, and also that Belt of Venus image that you had?
Well, you see, I have. If I can, see, I'm connected on the laptop, so you could see me. But if I connected via the same software, it would conflict. So I don't have that. I'm in the observatory, but you're seeing just the observatory. I can't do that because I'm just on the internet. I'm not on my software on that.
Yep. Okay. We are seeing that photo. Your profile photo. I don't have a live shot of you. We're just seeing this headshot of you with the Rosette Nebula or something behind you. Is that? I don't know.
No, we're seeing Rick live.
You are? Okay, I don't know why that is.
Yep. In all its glory.
How
I have
about
not.
that?
Yeah.
Yeah, I'm
And we're
not.
seeing what looks like the moon. We're seeing what looks like the moon out the window, but I think it's a reflection of your light.
It's a oh yeah, it's not, yeah, it's just a light bulb. Yeah, right.
Hey, hi, Rick. I had a couple of questions. I didn't realize I was muted.
Sure.
When you're looking at the explosion of stuff off the star, are they also able to look at the rate at which it dissipates when they look at it coming at you? Are they able to determine that, or?
Well, they can determine
But the
this.
further out it goes, the more it's going to dissipate. It's going to spread further and further and thin out and all. Can they look at that rate?
That's true. I know they do the speed. So they do the speed, and I imagine they can calculate that it's dissipating.
Uh-huh.
But of course, eventually, you know, like they'll look like 1987A, that one that went off, and that nova that went off in Large Magellanic Cloud. Eventually, they take a picture of it with the Hubble, and then they know, you know, what it actually looks like visually when you know, after it gets out big enough that they could actually take a physical picture of it. But of course, initially, it's really small, and you can only do. You know, it's amazing the information we get through a lot of what we know about stars comes from spectra. You know, the spectra of the stars. That's another thing that amazes me. That either we measured the brightness of it and learned something of it, like in exoplanets, or we measured the spectra of it and learned a lot from it from the spectra. And so most of what we know is either from spectra, either from photometry or spectroscopy. It's just amazing. I imagine there's a way to figure it out. It's just not. It's above my pay grade, I gotta say.
Yeah. We had one of our very first talks in like 1984 was a guy named Ed Orovak, who was a member of the AABSO. And I don't think he convinced too many people to do it, but there's so much additional stuff they seem to be doing now that's very interesting to hear about that.
Yeah, you know what? Their website is fantastic. If you go to their website, you see all this different observing sections, you know, and you can explore there. And not only that, they got a great YouTube channel. There's a young woman named Lauren Harrington, I think is her name is. She has a YouTube show that's named Spectroscopy on a Budget, I think it's called. And it's she uses a Dobsonian with what I'm using, a star analyzer. This girl does amazing stuff. It does her telescope doesn't even track, and she does what's called drift scanning. She just does amazing stuff, and her stuff is being submitted to AAVSO, and you know it's up there with anybody else's. It's pretty amazing. It's better than my stuff, I could tell you.
What YouTube is that, Rick?
They have their own YouTube channel, the AAVSO, and they have a bunch of YouTubes that are just fantastic. And you probably see it at their website, but if you go on YouTube and you search for either Lauren Harrington, or just search for Spectroscopy on a Budget. She says spectroscopy as if it's a photo. Spectrography.
No, that's what I'm saying too.
Yeah, say that 3 times fast.
Rick, I have a question. The first time I really thought about it is the inclination of the planet in terms of the occultation of the star for figuring out the distance of the planet from the star. So it seems to me the more inclined the orbit is of the planet, the more likely you're going to be able to tell how far away the planet is from the star. It seems like that would probably go down as you got more toward, like, say, an equatorial kind of occultation where you didn't see a high angle. I never thought about that before, but that seems to be, because I was always wondering how they come up with, you know, the distance of the planet from the star. But it seems almost like the more inclined it is, the better your chance of picking out a distance from the star. And then, of course, the other question in that regard is, let's say you have a planet that supposedly orbits the star like in 4 days, like you said, are there enough people going back and are they able to check it every 4 days to see that it occurs? Because I know there was one speaker we had a long time ago, and one of the questions I asked him is, with some of the satellites that we're doing like once every couple of years, on a star was, how do you know it wasn't just a piece of random space junk that went by in in interstellar space that occulted the thing?
But yeah, that's a great point. This, the observations I showed you are, that's old data, in fact. I'm sure there's more observations of that star between when I took that in 2017 and now. And not only that, the database is so much more better organized than it ever was. That actually, the thing I showed you, I think was from like Czechoslovakia has a database going. So it was a private database that I just I was told to check out because of what I was, my thing was 16 minutes late and I couldn't figure out why. And so that was the only place at that time to figure it out. Now I would go to the AVSO and download data from them and figure it out. So they watched, again, there's that list that they want you to watch. Let's face it, there's not that many people doing it. At the time I started, there was only, I think, 80 people worldwide doing this.
Wow.
It might be more, it's probably more now. It might, it could be hundreds for all I know. But when I took the, it was an online course you could take to get going on this. There was only 80 people at the time that had taken it. But I think it's just a fantastic thing. But like you said, the angle, let's face it, you're never going to see, a perfectly aligned orbit to the Earth.
Yeah.
So I think mine was 87, 86 degrees or something like that. But you're right, it comes into play. It certainly comes into play when you're determining the orbit around the planet around the star. Yeah.
Yeah, because I never thought about it. If it goes in front of the star, it really does matter in terms of figuring the orbit, how far off the center it is.
Yeah.
And I was wondering how they were coming up with, what the how far away from the star it was and all that sort of stuff. But that explains it. Yeah. And Ed Oravac at the time was talking too about, again, the use of, and this is 1984, so it's like almost 40 years ago almost, was talking about how valuable it was for the amateurs to be doing these observations. And they were just basically doing by eye a comparison of a variable star with the reference stars that were nearby. And that was still valuable back then. So it's interesting to see how much more sophisticated it's become.
There's people today that were doing NovaCast visually. So you go to their database, you could put in NovaCast, bam, you see, there's hundreds of observations. Some of them it says VIS, and it is done by visual. And you can get within a tenth of a magnitude doing it that way.
Wow.
They got data going back 100 years on some of these stars. But anyway, they had photometry through CCD. They have visual. They have all different these methods, but they're labeled. If you use a special filter, a photometry filter, you put that in there, or if you have no filter, you put that in there. But there's still. I was surprised, but there's still plenty of visual observers out there.
So it sounds like if you're a good visual observer who've done it for a while, you're going to be within a tenth of a magnitude. That's pretty damn good.
Absolutely, yeah, absolutely, yeah.
Hey Rick, I went to that site, and you're not kidding about that gal. It's not even a big daub, but just very quickly scanning through the information and the chart she's giving. They're pretty intense stuff. And then she showed the equipment, the basic eyepiece that she's throwing in this thing. I don't know how she keeps the daub weighted, but it's a really fascinating site and a very quick look.
Absolutely. They have a bunch of good videos, YouTube videos, a bunch of them. And it's not just on spectroscopy. You name it, they got it on it, whether it be the variable stars or spectroscopy. Just I couldn't believe how good it was compared to in the 1980s, we had the guy come to Greenwich from Stanford, and he was the big variable star guy back then, Charles Scoville.
Yeah,
Charlie. He gave the demonstration. I thought it was fascinating that the way they did it. I didn't realize how they did it, the visual comparison, where they have the star chart and it shows you all the comparison stars. But yeah, it didn't click with me then. I wanted to I want to take pictures, back then. So
that was the main thing. That was the main thing Stanford was trying to do at the time.
That's basically all they did.
Yeah, exactly. Yeah,
Charlie. It's the reason why I didn't join the club, because to me, astronomy is multifaceted. I don't want to zero in on one thing.
Yeah.
I want to see, I want to see planets. I want to see nova. I want to see galaxies. So to me, and that's all they did, because I knew members from their club, and at the time, I think that's all they would push is just variable star, variable star, variable star.
Yeah.
And they did great work, but you know, that's why I didn't join their club.
Well, I surprised Charlie one time. He didn't know about V Aquila. But I think Ed Oravec ultimately was kind of disappointed in our group that we were not all wanting to be variable star observers. But I agree with you that, you know, you got to look at a whole bunch of stuff, and it is a very wide field, and it's a lot of fun to do the whole thing. Yeah. But if you get the passion for it, you get the passion for it.
Yeah, you get the bug. You get the bug. And I got the bug now for asteroids, and I got the bug for exoplanets. and the neat thing about asteroids is you don't have to. It's like doing a variable star, because they came to our observatory and they did variable stars while we were there, and you know they had the thing by heart. They you know you get to know a star so good, you memorize the reference stars. So they showed us how to do it at the moment. And it was fascinating, but you know, it just wasn't at the time. It just wasn't me. I had so many other things I wanted to explore.
Hey, Rick, talking about Stanford, what's going on up there? Can you update us on the status of what they're doing at the Stanford Nature Center?
The plan is they're going to attach a planetarium to the observatory and completely redo the observatory.
Wow.
And so now it's in limbo. I haven't been there in quite a bit, but it's in limbo because they're going to make a huge science center there, planetarium built in, digital planetarium, and an observatory attached, one big building.
Wow. They keeping the original scope with the Perkin-Elmer optics and all?
There's talk of getting rid of it. There's talk of keeping it. I don't know what the decision is yet.
I thought it was gone. I thought it went to New Mexico.
I thought it's supposed to go to Arizona, but I don't know. Does anybody, whoever spoke up, did they know for sure it's gone, or?
I was told by somebody that it went.
I should go look, but I haven't.
It's the third largest. It's the third largest MAC in the world, I think.
Max Satov, yeah. I think it's the second largest in this hemisphere. I think there's one in South America bigger. But anyway, the last I heard, it was in limbo. I didn't know if it was taken or not. I should go because I worked on that observatory. I mean, worked on that telescope. I brought it back to life practically.
I don't.
Yeah, the one at Harriman was supposedly the second biggest in New York State, but nobody knows whether that's there or not either now anymore. It's on a private property. We're losing them.
Yeah.
I think the last I heard about that was, I thought Zane was talking about that when it was talk of it going out.
I think Zane was the one who said it was gone.
Yeah.
He said it was gone or going.
Yeah, Zane had told me that too, that he thought it was going to New Mexico.
But that doesn't mean that it's gone, that it actually happened, I guess.
Well, somebody's got to take it off the mountain. It weighs about 1 billion tons.
Yeah.
And of course, the problem with a MAC that big is the mirror can never cool.
Uh-huh.
Yeah, to get that out of there is going to be a job.
I looked through a 20-inch MAC out in a private observatory in Arizona in 2011. And the counterweight was a gigantic ball of concrete that weighed 600 pounds.
Well, thankfully, that was a fork in Stanford because no counterweight there, but it's massive.
So Larry, basically, Larry, you looked through the largest porta ball ever made.
Well, but it was this huge thing sticking off the end of it. I mean, it was amazing. It was all gigantic pipes and all sorts of stuff.
I thought porta ball was a pretty good idea, Mike.
A guy had one Saturday night.
Okay. I didn't see it.
He
Rick.
the Meg 1 porta ball that was.
Rick, I got a question on the spectrography. How easy or hard is it do you find to create the baseline? You use Vega and then you have a fix
Yeah, you're always just supposed to, and by the way, there's about 30 videos at the field, what is it called? Field tested, what was the name of the darn thing? I can't remember. Field tested equipment, I can't remember.
You mean Tom Fields?
Field tested systems. If you go to their website, Field Tested Systems, there's about 30 videos. The first thing they want to tell you is you start on an A star because it has strong absorption lines. And then you get the feeling of focusing. You believe it or not, you do not focus on the star. You focus on the spectrum. Remember, the spectrum is spreading out unevenly. The red is going to go a farther distance than the blue. So you kind of focus on where you're interested in or where the feature is. If you have a feature in the blue, you focus in the blue. If you have a feature in the red, you focus in the red, or you focus in the center and take your compromise there.
You talking about Tom Field's website?
Yeah, Tom Field.
Right, I know.
Field Tested System, it's called. Field Tested.
Yeah, I know Tom, and I got his software and stuff and equipment and the star analyzer. And I did some stuff. I haven't done anything the last year and a half. So.
Oh yeah, it takes some getting used to because you got to get your your separation right from the device, and then the focusing is a little bit. You know what I do? I use SharpCap. I do everything through SharpCap. And then I get the result and I put it into RSpec. But and if you want me to send you, I got documentation that what I use. I could send it.
That'd be helpful. Yep, that'd be helpful.
And it's Rick Bria 22 at Gmail. You email.
I have you on the database because I sent out the e-blast.
Okay. Oh, okay. Good. Yeah. I could send you, the system I use because in SharpCap, you could zoom in on the spectrum, and while you're at the scope and focusing, and then it takes a lot of the guesswork out, especially if you're like me and you need, you don't see as well as you used to. Yeah.
Well, it came out fine, but I was using my camera and which is not easy because I was using a zoom lens. So you got to keep it at the same zoom focal point for every star after that. And
yeah.
If you can't not watch my lenses, so I guess it's easier on a telescope when it's a fixed mount lens, right? A fixed lens and not a zoom.
Right. So you got the device in front of the zoom lens, right?
Yeah. I bought both. One for the SLL, but I also bought the one to get started. I told Tom that give me also a piece for the front of the lens because that's a good way to get started to learn.
Actually, you can get some good resolution. You have to stick to bright stars, but you can get really good resolution.
Yeah, I gave a presentation to the club, I guess 2 years ago in September. In the background, and I showed some pictures of what I got. It worked. It came out okay.
Yeah, if you stick to bright stars, it's a great system. You're doing it.
Yeah. It's not expensive either.
No.
I'd just like to observe that if we actually had the backgrounds that Frank and Rick have behind their pictures, we wouldn't be here now. We'd be out looking at this stuff.
Hey, that picture I actually took on a camping trip, and all I used was my tripod and my camera and one shot. And then I put it into.
How much time did you put on the exposure?
I actually calculated out. You can't do more than 15, 20 seconds, depending on the length of. I actually calculated so you don't get star trails. So I actually measured it out. I forget why. There's a formula.
Because Palladini had something similar up at Mike Safola's place in Vermont, and I forget how long his exposure was. But yeah, it's like it was like the Southwest supposedly. But again, when you're looking at it naked eye, you don't see it. But it's an awesome photo. Jeez.
Yeah, 15, 20, and then I put it in the Photoshop to bring it. Well, I use Affinity Photo. I've done Photoshop and Adobe software. I'm one of those people. Adobe cut the chain, because it had that pricing. And Affinity Photo is just as good. They're fantastic people.
Wow.
And they do, by the way, their Photoshop program, the equivalent, has something in there for astrophotography built into the software.
Okay, all right. Hmm.
All right. Any other questions from anybody for Rick? Any
Not me.
need clarification? Because I thought while we have a bunch of people, anybody else? I didn't, did I miss somebody? I thought
Just came into the room.
what I thought is I'd ask Rick, I have that astrospheric and what was it, clear, what was it, clear sky? Not clear skies, clear, anyway, I've got them up. We could take a look at them if you want to show us around a little bit. What do you think? You can just point out.
Yeah, absolutely.
Let me just make sure I've got. Let's see if. Yeah, here we go. Okay, so I wanted to point out we are trying to get our YouTube channel going. We have Westchester Amateur Astronomers. I've put Larry's terrific talk from last week up on that channel. So anybody who missed that or wants to go back up and back over it and take another look at his grand tour of the universe, that's up there. And also the talk that he did about the astronomy on the ceiling of the Grand Central Terminal building. We'll try and get some of these other talks that we have recorded and get them up there. There's another Westchester Amateur Astronomers YouTube channel which has our slideshow, and the one that I can log into is this one. I don't know where the other one is, but we'll have to, at our board meeting, maybe we'll try to figure that out. That has the one of the older versions of the slideshow on it. But let's see if I can go ahead. Let's go. This is Astrospheric, astrospheric.com. And I don't know if it's just for New York City, but I don't know my way around this. Rick just told me about this. But Rick, do you want to just point out anything that's of note here, why you like it, and we'll look at the Clear Outside site after this?
Yeah, well, first of all, you have the graphic, and if you use your mouse, you use your keyboard, you could. You don't want me to share a screen, right? You just want me to talk.
Could, if I have it up, but if you want to go ahead and do it, it might be easier if it's easy for you to get that up. Maybe you do it and then you show us around on your, that way you'll have control over the screen.
Right.
So it'd be a good way to share this with the rest.
Okay, it says you gotta stop sharing.
Yep. Okay, there you go. You should be ready to go.
Let me see if I could do it here.
See, now I see the picture of the observatory as your virtual background, Rick.
I got my laptop doing that.
Yeah, I'd love to see that picture you took of the belt of Venus too, if you can get it.
All right, so let me go to. I can't do it from here. Got to do it from here. Here it is. Okay, here's Astrospheric. Everybody seeing that?
No, it's not shared yet.
Let me see here. Share. That, you seeing it now?
Yes.
Okay, so you have the usual thing like you get a clear sky chart. You have this thing that indicates how much clouds you have, the transparency, and the seeing. But in addition, you have, and this is updated, by the way, twice as often as clear sky chart. So the data is never 12 hours long, old. And then you could go forward and back and see what the prediction is. Just like you could. Well, I don't think you could do that clear sky chart, can you? I haven't used it so long.
No, I think you only get the upcoming 48 hours.
It even tells you what's going on in the sun, this KP thing. I don't know if you see what we're making. It tells you when the moon is going to come up, when the sun is going up, the wind direction, and I should get this out of the way, huh? Right over there. So seeing, transparency, whether it's below average, cloudy, all that stuff, the wind and temperature and dew point. But the thing to me is it's updated twice as much. So I could tell you from experience, it's more accurate than Clear Sky Chart. I don't know if anybody.
Is
Yeah.
this downloading the app, or is it because every time if I just put in it.com, I get sent to the Apple app?
No, it's right on the internet. I'm at astrospheric.com. I didn't download anything.
Huh.
Yeah, I had it on the website too. I was just on a web address.
I didn't download a thing. Clear Sky, what do you call it? Clear Outside is an app. It's also on the website. I'll go to Clear Out. If everybody's done with that, I can go to Clear Outside right here.
Yeah, that one is actually that one I'm getting is on the internet, but the Astrospheric keeps taking me to an Apple app on my iPhone.
Maybe I don't know what the deal is there, but
Mike, I just tried it on my iPhone. It popped right up on the website. So it could be the browser.
so this is maybe the browser. This is Clear Outside, and this is actually more accurate in my view than the Astrospheric. The neat thing about this is it gives you high clouds, medium clouds, and low clouds. And sometimes the high clouds, in this case, look at this, high clouds is, so it's, that hazy clouds is not really cloudy, but they got that hazy clouds. And then the low clouds, which would be the thick ones, are at 0. But it's a more accurate representation of the sky if you followed it. And by the way, this is updated on the hour. So as far as I know, it's updated on the hour.
Rick,
And,
how would you compare this to something like a classic, like Clear Sky Chart for accuracy?
I say it's way more accurate because it's experience. I've been testing them all together. Clear Sky Chart, if you know, it's only updated I think it's either every 12 hours or 6 hours. I can't remember.
12 hours.
12 hours. All right. So I can tell you the Astrospheric is updated every 6 hours, twice as much. And this claims to be updated every hour. And if you checked this morning, if you check the day of the eclipse, this thing was bang on. It said there was going to be those high clouds. It says when they were going to be. By the way, if these were green, it'd be good viewing. So they give you that color thingy up here too. So we have no green. Obviously it's going to be cloudy for the next, God knows when. And you can go all the way down here, and it gives you humidity and dew point and temperature and wind speed and precipitation. But of course, the things we're worried about here: visibility, fog, chance. Like you got a chance of fog here. But the thing is, the clouds I think are way more accurate. I want to say by a factor of 2 than anything I've seen before.
There's also a very nice site called SpotWX. SPOTWX.com, that gives you a whole bunch of different prediction sites from Canada and the United States. And they have short-term predictions, medium-term predictions, and long-term predictions, and the display is graphic.
SpotWX?
SpotWX.com. And
it's just a raw model output, but it's very detailed and hourly or 3 hourly, depending on how often the model steps are.
But the nice thing about it is the display is graphic, and some of them do have the low, medium, and high cloud.
Right, the high resolution models.
Because you need that, you really do.
Yeah, that's what's really nice about Clear Outside. That they have those layers. I'm not certain it's more accurate, but it certainly has greater precision.
It seems from the tests that I've run, I mean, maybe sometimes it isn't, but from the tests I've run, and I've done quite a bit of comparison between the two, but I think it's hands down. I'm not saying it's going to be a dramatic difference, but it seems to always be better. Almost always be better than Astrospheric, and Clear Sky Chart I think comes in last in because it's just so many times the data is just so old. I mean, you know as well as I do, anywhere near New England or New York, things can change on by an hourly basis, or certainly by 3 hours. There's some times when I'm going to go out to observe, I don't know whether 2 hours ahead if I'm going or not. And
Yeah.
same thing with the eclipse. You really
Rick,
know
you don't like the weather in New England? Wait a minute.
You just don't know sometimes. Anyway, so that'd be my recommendation anyway.
I use this thing called Good to Stargaze, and you could put in the parameters that you will choose, to give you the accurate or the, did you go or not? And it does do a, for the free version, a forecast. And I find, it's probably not as good as that one, but, for quick pop up on my iPhone, and you could put in any location and it'll tell you. So.
It's called what?
It's called Good to Stargaze. You look at my screen. Yeah.
I could see it. Sort of.
And you can, these parameters are adjustable. So you could say under a certain temperature, a cloud, you could say good or bad, yes, no. And you can adjust those things any way you want. They'll calculate it out and tell you, you're good to go or not.
Let me stop my share here. Stop share.
Yeah. What bits and pieces I've learned about these different methods is that I think atmospheric, although I just looked at it first time tonight, clear outside and the our old the old standby clear sky chart are all run off the Canadian model. I think the Canadian models run every 6 hours. So any, and they run, hourly resolution on them, which is one of the things that they, do work with very well. Some of the model output is only every 3 hours from the American models, but spotweather.com is kind of a fun site for almost anything you want that you're looking for. But it's the raw model output. It's not modified for anything. I don't know if these other ones are modified based upon model experience or anything like that. And I haven't done what Rick's done and actually done any real comparisons with real data, except for, of course, this past event, which we looked totally overcast in all the models at 5,000 feet for yesterday morning. And it wasn't, fortunately.
All right, well.
On a different subject, Rick's showing the Venus transit brings back some old lore from the WAA about his trip out to Pennsylvania to get that photo, along with a few of our friends. And about Mr. Safola talking about how you guys were going into stores with maps showing all the airports, asking where's there an airport around here we can go to, with a truck full of stuff that looks like missile launchers.
At 3 o'clock in the morning, as we're trying to get with June 8th, right? It was June 8th, so it was the same, the same phenomenon that was going to happen at the break of dawn. Earliest sunrise of the year.
But people were sort of feeling like they were going to get arrested from the questions that were being asked.
I think Mike was Mike wanted to distance himself from us. We were
the best was when we went into their version of a 7-Eleven, and Rick asked if there are any small airports near where we are, and the lady said, well, there's a small one not too far away, but I don't think it's used anymore. And Rick goes, that doesn't matter.
Yeah, he said, any airport will do. I think
any airport will do.
Any airport will do.
And you have that computer with every airport circled in red, Paul. I mean,
this was 2004. Tooling around in a car with a laptop was, that was cutting edge technology at that time.
And then we were thinking about setting up on some poor schmo's lawn because we were hoping they wouldn't be up while we're all set up with the equipment. But I'll never forget, Paul, seeing that transit, seeing the black dot naked eye against the sun. No optics, nothing.
As it was rising, yeah.
Yes, that was incredible.
That was
Yeah.
That's one of those things that you would have. I mean, and Bob Davidson at the time also said the same thing from from the Palisades Parkway. Is like if you read that somebody in antiquity had seen a transit of Venus naked eye, you would have said no way. But if you have enough cloud cover at that point, you can see the disk of the sun and the transit taking place naked eye. And that was a proven thing, but I don't think anybody would have believed that otherwise.
it was so distinct, and it was just it was remarkable.
It was a good photo too you got there, Rick. Yeah.
Yeah, there was some good pictures that came out of that, and a little video from that trip.
Yeah, the video was spectacular. Remember the video of it?
Yep.
Through the C8?
Yep,
Yeah,
I think we threw the old Mintron in that Palladini had turned us to.
Yep. There was some. Yeah, I think I still have that video. If you guys want to relive it sometime, maybe if we need some filler at the members.
Well, if you can turn that into a YouTube, might be good.
Yeah.
I also remember the first time you and me, Paul and Rick at the I guess at the time the Bowman.
The Bowman, yeah.
We put the Mintron in and we put it on the Orion Nebula, and at first we weren't even sure. It looked like it was all fuzzy, like something was wrong with them. We realized it was so big, the nebula, we were getting the whole thing. We had to lower the power.
Like, what's that cloud? What's that cloud in the way of
well, we had that good thing with the up at Pound Ridge with the it was the moon occulting the Pleiades or something that time.
Right. Yeah.
Was
one of those early uses brought a TV set, plugged it into a car battery adapter, and used the Mintron to watch the moon occult the Pleiades. And it was one of the early. Larry, we actually beat you with your setup, and had a bunch of people coming over thinking we had something we had recorded, that it wasn't real.
And it was something that you could not do visually because everybody's like, "Oh man, that star just got occulted." It's like, "Oh wait a minute, I didn't get to see that." But with the TV, everybody was seeing it. It was like great, yeah.
But Rick, that's incredible. That's just incredible stuff you're doing, and I really enjoy that you're doing a number of these different scientific processes with this equipment, as opposed to just one area, which some people do get hooked into.
Yeah.
Well, I'm working for a school, so I want to expose. In fact, most of the stuff I'm doing has been with a student. The variable star was with a student. The asteroids were with a student, and so I'm trying to be versatile in what I'm doing, because you never know what a student is going to ask. I want to do this. I want to do that. I want to try this. I want to try that. So. I'm having a blast. I got to tell you, I'm having a great time. I think it's very rewarding.
I was just going to ask Rick. You were talking about the students before. It's like, how are you getting the students? How is this working with the school and yourself and all that? That you get students that are interested in this and want to work on it.
Well, I'm working part-time at a school, and they have an observatory and so I.
That's the Bowman?
No, this is it's called the Sacred Heart Greenwich. It's near the Westchester Airport. And so what I do is I take a picture, or I take whatever I'm doing, whether it's spectroscopy or exoplanets or whatever. Take a regular picture of a galaxy, and I send it to everybody in the school, and I say I did this, and I did it with this procedure, and I took that procedure, and just to kind of spark interest of what you can do at the observatory. Mm-hmm. And then I work with teachers that are, because I'm not a teacher, I'm a part-time tech. I work with teachers that are teaching, whether it be chemistry, for the spectra, or physics or something like that, and so they'll have a student say, "Hey, I want to try this, I want to do that. How can I?" And then I help them do it. Mm-hmm. I've had students here all night. I've had students via Zoom all night. This year was, believe it or not, it actually worked out better with the I hate to say it, with COVID, because the student didn't have to come here physically. Mm-hmm. We could do the work together. They're home via Zoom.
Yeah.
And we're doing they're seeing how it's done, and they're getting the data. I tell you, I worked with a sophomore that won an award for from New Haven, a New Haven club. I think it's New Haven. I forget what their name is. New Haven Astronomical Society or something. For that asteroid I did, but we found that double event with basically a chunk out of the asteroid. So she won an award for that. She did a presentation. She was really, it's amazing what a sophomore knew. She completely absorbed everything that we were doing. And when I was a sophomore, I didn't know 1/10 of what she knew.
Is this a high school or college?
It's K through 12.
It's a high school. Okay.
Yeah, high school.
Wow. That's very good.
It's a great observatory. It's and we just finishing up getting everything installed and calibrated and all that stuff. So then we're going to go after exoplanets, I think.
Wow.
Yeah, you say exoplanet to students, and I think that sparks an interest, but probably more so than asteroids.
Yeah.
All right, guys. Well, I think I'm going to call it a night. I'll just leave the meeting open. Any of you guys want to stay on the Zoom call and chat and stuff? Rick, once again, I just know you put so much work into getting this ready, and I really appreciate it. And congratulations on a wonderful talk, and on all the work you're doing and all the accomplishments. That's really.
Thank you very much. Yeah.
Yeah. Thank you, Rick.
Yep, I second that. Thank you, Rick.
Great
And
stuff.
anybody needs any help, and I got documentation. I could help you, no problem. We could do it.
Yeah, I'll reach out to you, Rick. I'm Frank_Jones with Rising.net. I'll reach out to you.
Okay, great. Thanks, everybody. Thanks for having me.
Thank you, Rick.
Thank you, Rick.
All right. That's Marianne and the girls. See ya.
All right. Thanks a lot, Rick.
Thank
Good night,
you.
all.
Night, everybody.
Night.